All right, we're going to look at an algorithm that will help us find the greatest common divisor of two positive integers without having to get their prime factorizations. And it's called the Euclidean algorithm. So let's see if we can do this to find the GCD of 288 and 108. Dealing with rather small numbers just to kind of get the point across. To establish the algorithm. Now, I'm not going to give you pseudocode for this algorithm or anything. I think it's best to illustrate by example. And not only am I going to show you how to do the algorithm, I'm going to describe why it's working as we're going as well. I think sometimes that's left out when we look at the Euclidean algorithm. So the first thing we're going to do is, and you know what, I think I'm going to type because the symbols aren't too bad and you can read my typed hand a lot better than my handwritten. So let's see here. Let's let x equal the greatest common divisor of 288 and 108. And our objective then is to figure out x. Well, we're going to divide the bigger number 288 by 108 and rewrite using the division algorithm, which says that 288 equals, well, 108 goes into it twice, so 108 times 2, which is 216, which gives us a remainder of 72. Okay. Now, what's interesting about this is I can also rewrite my 72 then. So 72, if I subtract over, I can get 72 by itself. So 72 is going to equal 288 minus 108 times 2. And what I want to emphasize is what's happening here when we're doing this. So x is a divisor of 288 and 108. X is a divisor of 288 and 108. Well, x is a divisor of 288 and 108. Since x goes into both of these terms here, x goes into this term minus this term. X divides this difference. In other words, x actually divides 72. Because if x goes into 288 and 108, x goes into the difference of those, which means 72 is the difference. So x goes into 72. So x divides 72. Well, 72 is smaller than either one of the original two numbers. So 72 has to also be a divisor of x has to also be a divisor of 72. So to reduce this to a simpler problem, x goes into 288, x goes into 108, but now x also goes into 72. So now we can think of x as being not the GCD of 288 and 108, but we can think of it as being the GCD of the smaller number 108 and this new number, the remainder we got, 72, because we know that x goes into both of those. Okay? Now, let's repeat the process. Divide the bigger number, 108, by 72, and rewrite it using the division algorithm. And I don't know what's going on with this program. It keeps repeating parts of things I type on its own. So if you see me backspacing, that's why. So 72 goes into 108 once. So this is going to be 72 times 1. And what's left over is 36. And now I can rewrite my 36 by subtracting. So 36 is going to equal 108 minus 72 times 1. And we already know that x goes into 108 and 72. So x has to also go into 36. X divides 36. X divides 36. Well, now, if x goes into 36, then x could be thought of as the GCD of 108, 72, and 36, which means it has to be the GCD of the two smaller numbers. We don't need the 108 anymore. So x is the GCD of 72 and 36. Now, at any point along the way, if you know the GCD, then you're done. But I'm going to work this problem all the way through so you can see what happens. For example, The greatest common divisor of 72 and 36, you might realize, is 36, so we'd be done. But let me go ahead and finish this off. Divide 72 by 36, and we can see that 72 equals 36 times 2 with no remainder. So now, what does that tell us? This is a little bit different than the other cases. That tells us that 36 divides 72. That means that x divides 36, but 36 divides 72, so x could be 36. So when you get to no remainder, then x has to take on the smaller of the two numbers. So if one of these numbers here is a multiple of the other, then the smaller number has to be the greatest common divisor. So x equals 36. And finally, since x is the GCD of 288 and 108, we know that that answer is 36. 36 is the greatest common divisor of 288 and 108, and we did not have to find any prime factorizations to get that. All right, I kind of fumbled around my words there at the end. I hope that made sense. 36 went into 72 evenly, so 36 is the greatest common divisor of those two numbers. So that's how you know to stop. Let's try another one with different numbers. Determine the GCD of 123 and 278. So we'll start the same way. Let's call that GCD X. And let's divide the bigger number, 278, by 123. Well, 123 goes in twice, so 278 is 123 times 2. So that's 246, which has a remainder of 32. And then we can subtract to get 32 by itself. 32 equals 278 minus 123 times 2. And since x divides evenly into everything on the right side, x divides evenly into 32. So now, if x divides into 32, then x could be thought of as the GCD of the smaller number from before, 123, and this new small number, 32. It's the same x, so let's divide 123 by 32. Well, 32 goes in, I think, 3 times, which is 96, meaning we have a remainder of 27 left. Okay, and you might be catching on. You don't really have to rewrite the 27. The conclusion here is going to be that x, our greatest common divisor, has to divide 27, the remainder. So let's think of x as being the GCD of the previous smaller number 32 and the new small number 27. Now again, you might know what the GCD is and you could stop and write it down, but I'm going to finish the algorithm all the way to the end so you can see what happens in different cases. In the last problem, we got two numbers where one was a multiple of the other, so you know what to do in that case. In this problem, we won't see that. Let's divide 32 by 27. So 32 divided by 27 just gives us 1. So 27 times 1 plus a remainder of 5, which is going to tell us that our greatest common divisor has to divide 5. So x is going to be the GCD of the two smaller numbers, 27 from before, and our new small number 5. Divide 27 by 5. 5 goes into 27 5 times with a remainder of 2, which means that x divides 2. All right. So x is going to be the GCD of the two smaller numbers, 5 from before and now for 2. So divide 5 by 2. Again, I think you get the point of this. It's an algorithm. It just repeats. And once you catch on, you can speed things up, but I'm trying to be as clear as possible. So 2 goes into 5 twice with a remainder of 1, which means that x divides 1. Now at this point, x divides 1, which means that, well, the only positive integer that goes into 1 is 1. So therefore, x has to equal 1. So finally, the GCD of 123 and 278 is x, but x is 1. So this is another case for finding the GCD. In this case, you don't ever get down to where one number is a multiple of the other. You just eventually get down to where x divides 1. So the divisor, or the greatest common divisor, has to be 1. So that's the Euclidean algorithm. No prime factorization is necessary, just repeated applications of the division algorithm, in particular with a focus on the remainder, because the remainder takes the place of one of your inputs to the GCD function, and you just keep processing it until you get to such small numbers you can easily find the greatest common divisor.